this is Mr. Watlington, and we're back for Chapter 2. Yes, right, Chapter 2. And this week, in this lesson, we're talking about hardware and software of our information system. All right, let's jump right into this. All right, here we go. So, some things we're going to talk about in this session is some of the components of a computer, whether it's hardware, software. We're going to look at cloud computing, some of the different types of technologies I'm going to touch on, virtualization, storage, mass storage real quickly, and we're going to do a quick overview of networking. All right, so when we think about a computer, some of the basic processes that a computer does, it takes an input, it processes it, it gives it as an output, and then it stores that. So when you think about input or input devices, things like your mouse, keyboard, webcams, all of those are input devices. And when we're at the processing side, we're really looking at our CPU and memory and things like that. We're going to talk more about that. The items in red are some we're going to get a little deeper into. Output. That could be a monitor, printer, all those types of devices. And storage. When we talk storage, now we're talking hard drives, optical drives, and SSDs, those types of things. So when we think about your basic computer design, really at the bottom of the stack, I like to decompose a computer into these layers, these sections. At the bottom of the stack, that's our hardware. And when we talk about hardware, we're talking about the CPU, hard drives, the memory and monitors, all those things that make up hardware. And then on top of that, we have an operating system. So you have hardware, and then you install an operating system, whether it's Windows, it could be Mac, whatever, but that is installed on the hardware. On top of that, we have our applications, our computer applications, such as Office or Adobe, any of those type of applications. So we got hardware. On top of hardware, we install operating system, and on top of the operating system, we have applications. And those are the basic layers of pretty much any computer. And then we, the users, we interface with applications. Now, why is that important? Because if we look at these layers, really, this kind of shows us how we demarcate and how we secure computers, meaning that applications don't talk directly to the hardware. Applications have to talk to an operating system. So from that's a layer of security that's built in, so that if I have an application that may have a virus or some type of malware, it makes it more difficult for that application to go in and infect the BIOS or some of the hardware components. Likewise, as a user, I don't talk directly to my hardware. Really, I don't even talk directly to the operating system. Actually, there's only about a couple of commands that we use, like Control-Alt-Delete. That is a command that goes directly and lets us restart our computer that talks to hardware. Otherwise, I'm talking through an application to the operating system, and then the operating system talks to the hardware. That's kind of how the layers are laid out. Okay, so we're talking about hardware, right? Let's dig into our hardware. At the heart of your computer is the central processing unit, or the CPU. And if you look at this is a motherboard, and right there on that motherboard, that's where your CPU is mounted. And depending on what type of computer you have all different types of hardware, all different types of motherboards. Now, when we think about it from a process perspective, really, your CPU is a pretty simple device, actually. It does 4 basic things. 4 basic activities go on within that CPU. First, it has to fetch code. It's a fetch command. It goes out to your storage area, your hard drive, and it gets the code, brings it, and fetches it. And there's 2 types of code it gets, like application code that it brings and stores at a location so it knows what to do. And then it brings the data that you're manipulating. For instance, let's say a Word document. You want to open up a Word document that you've been working on. Well, first, you have to open up the application of Word, right? And then you have to get the document itself. So there's actually 2 sets of data that's being pulled up onto your hard drive, from your hard drive that it has to fetch. Then it does the decode. The decode function, that's where it figures out what the program is telling it to do to the computer, for the computer to do. So it has to do that decode. So it fetch, decode, then it executes. Then it actually performs the action that was requested, and after it finishes, it writes it back to the drive, back to the storage location. So that's the 4 cycles that your CPU goes through as it computes and as it does its functions. Now, the part of the CPU that does most of your actual computation and work is the ALU, what we call the arithmetic logic unit. And that's what performs the magic. That's where the secret sauce is. And really, it's not secret sauce at all. Actually, it's pretty simple, because it, believe it or not, as high tech as computers seem, really it is only able to do simple math. Add, subtract, multiply, divide. It just does that to a series of binary codes, or ones or zeros, we call it sometimes. So it's pretty simple. Now, how all this stuff is stored is in memory. Now, for whatever reason, when we talk about CPUs and motherboards, we call it registers. Now, a register is just memory. It's just like any other memory. Okay? All right, speaking of memory, wow, what a segue. Gosh. We're going to talk about memory, not to be confused with storage, okay? It's a fundamental difference between memory and storage. When we talk about memory, we're typically talking about like RAM, random access memory, volatile, non-volatile, volatile types of memory. So when we think about RAM, and really most of the RAM we use today is dynamic access RAM. Now that's a memory chip that, when you say dynamic, has to be refreshed periodically or it loses its data. Now, if you know anything about RAM, I'm sure you do, that when you turn the machine off, or it loses power, everything in RAM disappears. So when we think about, and the purpose of memory is to temporarily hold programs while the CPU is processing them. Unlike storage, which is long-term. Mass storage and your hard drives, your SSDs, that's long-term storage. RAM is short-term storage. Different types of RAM, like I said, you got SRAM, that's synchronized with your computer's clock. Inside of your computer, it has a clock, and that clock speed runs at, like a lot of them now, 2.3 gigahertz, that's the clock speed. So with SRAM, it is synced with that clock, so that memory is running the same speed. Other types of RAM, you got RDRAM, like I said, and it uses a different type bus that's a little bit faster. So it allows it to send and receive data on one clock cycle. Then we have DDR-RAM, like I said, that's where a lot of our machines have gone to now. And what that does is it doubles the clock rate. So it's actually able to run twice as fast also. So if your clock is a 2.3 gig machine, your DD-RAM is actually running, at 4.6. So that's actually, which means that now you're able to move information in that cycle, in that fetch, decode, execute, store cycle. Now I can move data in and out twice as fast to the CPU. So now when we talk about storage, which is not memory, we're talking about things like hard drives, SSDs, solid state drives, magnetic drives. And really now we're talking long term. Now most of your hard disk drives, not SSDs, like I said, what they are permanent storage devices. And that's made with platters, a little round disk inside of there, that's coated with aluminum and some type of magnetic medium. Now how do those things work? Let's talk about this for a second. So when you think about a hard drive, a typical hard drive, it's these tiny magnetic fields that's in an aluminum coating with that's called fluxes. Okay, and these fluxes are, let's go back to 5th grade math. 5th grade science. You remember, magnets, negative, positive, negative, and how they interact with each other. Well, that's what they do here. These magnetic fluxes that's on that platter, they're turned in different directions, and they switch back and forth, and it's called flux reversal. Now, when you store information on a drive, the right head, it actually magnetizes and it causes that flux reversal. Now, when I want to read it, my hard drive does, it reads those reversals. So if you look at the diagram, right down here, so you see you got a south and a north, and a south and a north together. Now, where these go in opposite directions, those are read as zeros, and when they go in the other direction, it's read as a 1. So you kind of see from the pattern how each one of these, as they turn, like the north together, that will give you a binary 1. A north and a south give you a 0. Even a south and a south together gives you 0. So that's kind of how, in a very simplistic manner, how data is written onto a magnetic media and how we're able to read it off because of the flux reversal. And the magnet and your head, the head that moves around that, is able to actually register and read those reversals. Okay, let's look at computer software for a second. When we talk about software, okay, there's a lot of different things, but we're going to start with just your desktop operating systems. And here's probably the 3 biggies. You know, you got Windows, the Mac operating system, and Linux. Not sure how many of you guys are familiar with Linux. I use Linux quite a bit, even at work or for things we do at home. So those are probably your big 3. And they all have advantages and disadvantages. And trust me, everything up here, all of this can be argued one way or another, meaning that the advantage for one person could be a disadvantage for someone else. But if you look at Windows, some of the advantages, easy to use, yes, because we've really institutionalized the Microsoft products. So they're pretty easy to use across the spectrum, from going from one place to the other. You know, it's good for gaming. It's you know, and you have the Mac, the Windows infrastructure in place, so you know the support structure is there for Windows. Some of the disadvantages, you know, is price. You got to pay for it. Stability, it's gotten better. You know, some of the earlier versions was not that stable, but yeah, it's gotten better. But and as well as security, and not that other. You know, whether Mac or Linux can't be hacked or cracked into. No, it's just that Windows, because it is so big, so institutionalized, there's just a lot of seams, a lot of places in there for nefarious actors to inject their own malware and do different things. Now, let's look at the Mac, the OS, the Apple environment. Like I say, some of the advantages of that, it's really good for graphics and music. As a matter of fact, everything I'm recording, all I'm doing today is on a Mac. I'm kind of a Mac guy because I do the video stuff and I also do music stuff as well. So, you know, I like Macs for that reason. It's a pretty very stable platform because the operating system is it's basically built for the hardware. The two are built to run together. Unlike a Windows machine where you know you have the Windows operating system, but you have registries and DLL files that try to make sure that it's capable of being run on a host of different platforms, whether it's Dell or Acer or you know HP, whatever the platform is. So and with that you run into some compatibility issues based on the platform you're on. Whereas with the Mac, your Mac hardware and your operating systems are a little more tightly coupled together. Some of the disadvantages, actually, it's pricey. You know, the cost of initially getting in on the Mac is more expensive. If you're a big gamer, you know, Mac really isn't built for gaming and things of that nature. So there's disadvantages there. Now, for the Linux world, like I say, I like Linux because Linux is a very, very usable operating system. Has a lot of applicability, you know, across the board. Some of the advantages, one is open source. What is open source? If you're not familiar with open source means that it's basically free. Most of the applications, most of the variants are free. Low power requirements. I mean, it's a very lightweight, you can get some very lightweight distributions of Linux that'll run on very small things like, I don't know if you've heard of this thing called a Raspberry Pi. It's a handheld sized computer that runs on a Linux core and distribution, Raspbian. And it is very good, very good. Like I say, you can, security, yes, it is very secure. Like I say, because you have a community of people who work to keep it secure. And it's because it's open source. Meaning that there's anyone can get a distribution and you can make your own distribution and make changes and publish it back out there. Some of the disadvantages, like I say, it's a lot of your software, it's not compatible if you're a Windows or Mac guy. Some people say it's hard to learn because one, there's so many different distributions, so many different types and feels and looks and feels of Linux out there. But all in all, that's just some of the advantages and some of the disadvantages. So now when we look at these operating systems, let's peel the onion back a little bit more. So when we think about an operating system, it kind of does 5 things. If you look at here in the middle, you know, the programs, it really is just the programs and the code is used to manage about 5 different functions. Okay, we talked about the CPU, right? How it controls the CPU. We also briefly talked about the memory, how it manages memory. It also controls files, and we talked about storage and how things are stored. I/O, input-output devices. Your operating system controls how your inputs and output devices, for instance, keyboard, monitors, USB ports, and all those input-output, HDMI, and how those things get in and out of your computer. And it also controls your networking. So, for instance, your network interface card, wireless, and how you're able to connect up to the bigger world. Now, when we talk about these things and how they work, I have an analogy that I'll always love sharing. Okay, see, I like to cook, and to me, a computer is very reminiscent of working in a kitchen. Yes, and here, let me explain. Okay, if you go into a kitchen, typical kitchen, what do you have? You have, countertop, stove, you have a refrigerator, all these things, right? All right, let's say I want to make a salad, all right? So first thing I'm going to do, I'm going to go to my refrigerator, open the door, get lettuce and tomatoes and cucumbers and celery and all these things I need for my salad. I'm going to bring them all back over and I'm going to put them on the counter, right? And then I'm going to grab my cutting board and a knife. This is representative of a knife. No, it's not a knife, but it's representative. And I'm going to start to cut, right? Well, think about it this way. The refrigerator, to me, that is comparative to my hard drive. Your refrigerator is there for long-term storage. And now look at my countertop. Countertop is like memory. It really is. Because that's where I bring things to work with temporarily. Now, anybody who's ever cooked, if you walk into a house, one of the first things, if you love to cook, you're going to look at, and what does everybody look at? Kitchen counter space. Because you want a lot of counter space. Why? Just like with your computer. RAM. You want as much RAM as your wallet can afford. Because if you got a small counter space, you know what that means? I got to keep going back and forth to the refrigerator, bringing a little bit of stuff out, set it out, and put it back on the cutting board and start to cut. If I have a lot of counter space, I can put a whole bunch of stuff out there and I can cut it up. And I don't have to keep going back and forth to the refrigerator. Well, see, that's the same thing that your computer does if you don't have enough RAM. If you don't have enough RAM countertop. It has to continually keep going back to the hard drive, grab a little file, bring it back, give it to the CPU. The CPU processes it, and then the CPU is sitting there waiting, like, okay, while it goes back to the hard drive, bring another file, and this process goes on and on and on. And that's why your computer runs slowly, because your CPU is waiting constantly for this. For the bus to go out, pick up things from the hard drive, bring it back. No different if I'm in the kitchen. Now the CPU for me in the kitchen is what? My cutting board. Yes, I lay the cutting board down and I start to cut on that. So you see, that's how I always like talking about computers as kitchen counter. If you talk to anybody about a house, give me a lot of kitchen counter space. I can make it work. I can have a small refrigerator if I have a lot of counter space. Or I can have a refrigerator out in the garage, a spare one. Anyway, did that make sense? It didn't? Sorry. It made sense in my mind when I first told it. Anyway, so as we talk about operating system, let's break an operating system down into its components. At the very heart of every operating system, whether we're talking about Windows or Mac OS or Linux or whatever it is, at the heart of that is something we call the kernel, K-E-R-N-E-L, like a kernel of corn, the heart. And the kernel is software that actually controls the process of how information is either written to the disk or how we retrieve it from the disk and how we move it up and down the stack. So that kernel is really the heart, that's the core. Now around the kernel we have our different types of drivers and APIs, application programming interfaces. Now what these do, they are the interfaces that talk to the operating system applications. And what are operating system applications? Well, don't confuse these with user applications like Microsoft Word, Excel, PowerPoint, and all those. But these are the applications that come with your operating system. For instance, if you just load up on your computer Windows 10 and nothing else, don't load up Office. Well, when you open it up, all those things that are resident within Windows 10 are operating system applications, such as the desktop, the that you open up to change your printer settings, accessories, the little calculator, snip tool. All these things are operating system applications. And some of those are visible that you can see. Then there's other applications that run in the background that does a lot of things that you never see as a typical user. Then on top of that layer, that's where we have our user applications, the Adobe, Microsoft, Office, email, and all those. Those are not a part of the operating system, but I want to put those up here just to be sure you understand where they fit in the bigger circle of things. So remember, when we talk about the operating system, we are talking about these components, oops, right there, the kernel, the API drivers, and the operating system applications. And then on top of that, we lay in our user applications. So when we think about operating systems, we also have to talk about the mobile operating systems. Because if you look at this environment, all your cell phones, because I know everybody's looking at me, some of you guys are probably watching me right now on a cell phone. Well, your cell phone has its own operating system in it as well. And over the years, like I said, we've had many different types of cell phone operating systems. Some have gone by the wayside, but many are still here, like Palm. I think Palm is gone. It was a great operating system. But some of the big ones that we all know is the Apple, the OS, iOS. Microsoft played its hand in trying to do the Windows Mobile. Sabian, actually, that's a very big one that's used in a lot of smaller Nokia, Samsungs, things like that. But really, a lot of these operating systems, guess what? They are based on a Linux open source core. Even like your Android. You have an Android. If you think about all the different flavors and variants of the Android operating system, like Lollipop and Cherry and all these different ones, they're still a Linux core. Now, not only do we have mobile operating systems, we also have embedded operating systems. As a matter of fact, if you look around your house or apartment or your Volkswagen van that you may be sleeping in, I don't know, because I know some of you guys are college kids, you probably have a lot of money. So you may, in your dorm room, you may be living in a dorm room. But pretty much everything you see around there, like your Roku device, your DVR, your cameras, and now washers and dryers, refrigerators, anything that has like a display, there's an operating system inside your car. If you have a newer car, guaranteed there's an operating system, probably Linux, an OS that's running in the background that's making that machine do what it has to do. Yeah, any of this, the newer appliances, all these things has its own operating system. All right, so let's switch gears here. We're going to talk about cloud computing. Now that we understand, we've talked briefly about some of the software aspects, hardware, and computer components. Now let's kind of open it up to cloud. Okay, but to do this, we have to go on a journey. Yes, the evolution of computing. Way back, probably before many of you were born, we used to have mainframes. And what a mainframe was, and you probably have seen this on some of these old movies, where you walk in a room and the room is just full of these big racks and racks and racks of computers and everything, and these big tape drives are spinning, and yeah, those were mainframes. And what the mainframes did, they did all the central computing, and you had what we call dumb terminals, not because they were stupid, they just didn't have a lot of things inside of them. Basically, all they were was a keyboard and a monitor. Right? The green screens, well, you may have seen those in movies too. But those connected to the mainframe. And so if you wanted to do anything, you had to talk to the mainframe. The mainframe was sending the information. Well, along the way, IBM, they were International Business Machines, was one of the first companies that came up with the idea, the concept of a personal computer. Technology was getting to the place where we could start scaling down the size of the IT components. Transistors were getting smaller and smaller and smaller and smaller. We could get more of them on a circuit card, and so we were able to bring the size down. So now we have this thing called a personal computer. So I could go in my home and have a computer that I could work on myself and do everything. I didn't have to talk to a mainframe. But the problem with that was, I couldn't talk to anybody else either. Just me and my computer. Well, I wanted to be able to connect up to the rest of the world. So around the 70s, mid-70s, 80s, around that time frame, that's when we started moving into this, what we call a client-server environment. So didn't really want a big mainframe, but we have these things called a server And now all of our computers connect to the server, and everybody that's on the server in our little network, in our work group, we could talk to each other. So we've evolved from mainframes, we went to personal computers. Now we've taken the personal computers, connected them to a server, and now we got a client-server environment. Then along came, in the mid-'80s, the web. Worldwide Electronic Bulletin Boards. That's what the web, that's kind of what the definition was. Because way back in the day, the web looked nothing like it looked today. It was just bulletin boards where people could post notes and memos and someone else could go read them. But then we came up with the web and web services. Now, how I like to explain the web is in generations. In web generations. When we first started out with web, like I said, web 1.0, and like I said, this was, 80s, early 80s, late 70s, early 80s. And it was just static, read-only, mono-directional, kind of the web pages. Started out with HTML and kind of, we start moving up from that. Then web 2.0, it became participative. We call it the participative web. It became bidirectional. Meaning that not only could I go out to a website and look at something, now I could actually get information back. That's when we started doing blogs and wikis and all these other things. So now I could communicate with the person on the other end of the site by sending them an email or a text or an RSS message. Then now we are probably where we are now in Web 3.0, which is called the semantic web. Now the semantic web, it is readable by machines and humans, and that's based on ontologies. And really, to look at how the semantic web comes together, we look at things like now, if you go, buy a bicycle on the internet, and you go to Amazon, or you just go look at it, you don't even have to buy it. And you notice the next time you go out to the internet, you start getting all these ads for bicycles, and you're on some completely different site. How did that happen? Well, that's what Web 3.0, when we're talking about the semantic web, where it's saving, it's looking at clicks, it's making machine-to-machine interfaces so that now it can start pushing you products that it thinks you like. So, what's the next generation? Well, it's called the symbiotic web, and that's going to be kind of a blended interface. And we don't even know what that looks like now. We're working on Web 4.0 now. But with things like AI, artificial intelligence, and all those things, you're going to see kind of more of what you're seeing in Web 3.0, but it's going to be much more enhanced as far as the human-machine interfaces between the webs and us. Which then takes us to cloud computing. But now when we think about cloud computing, it's almost done a full circle from cloud back to mainframes. Because now the cloud, we're centralized, like you think about Amazon, the AWS, we're centralizing everything into these central locations, and all you need is a pretty dumb device, like a phone, anything that can get to the internet and to get to your information. Almost similar to how we started out with the mainframes. So let's talk about cloud for a minute. Cloud computing. You hear this term everywhere, right? Okay, in the cloud. Rapunzel, to the cloud. It's everywhere you go, the cloud. What is the cloud? So the cloud gets its name, it's really a metaphor, because back in the day when we first started doing the internet, instead of drawing all these boxes of routers and servers, we say, you know what, that stuff exists, and we just kind of start drawing a figure of a cloud around that, so we didn't have to talk about that, and everybody knew that, oh, you're talking about that host of internet hardware. So that's where the cloud kind of got its name from. Now, I love this definition because this is the National Institute of Standards and Technology, NIST, definition for cloud computing. And I have to get my James Earl Jones, Darth Vader voice when I read this. The National Institute of Standards and Technology defines cloud computing as a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources such as network server storage applications and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. Wow. What a headache of a definition. I don't even know what that says myself, and I'm working in this industry. I like to call cloud, this is my definition. This is my definition right here. It's a really cool service delivery model. Yeah, a little bit easier definition to remember. A really cool service delivery model. What do I mean by that? I'm glad you asked that question. Okay, when we think about a service delivery model, that talks about how can I get services to someone. Let's think about Pizza Hut or Chanello's or pickup delivery pizza place. They have a service delivery model. Domino's, that we will deliver in 30 minutes or your order is free. That's their model, that you call and we deliver. Well, the cloud is the same thing. Sometimes we get caught up in the technology. We think it's all about technology. No, it's really about delivering service to a customer. And the way we do this, we break this model up into 3 layers. Actually, there's more, but these kind of the three basic ones, where we deliver software as a service, we can deliver a platform as a service, or we can deliver infrastructure as a service. That's called the SPI model. I wonder where did they get SPI from? I don't know. SPI, software as a service, platform as a service, infrastructure as a service. So what does that mean? So when we think about software as a service, Gmail, all your Google stuff, that is software. Facebook, software as a service, meaning that you can go to Gmail and you don't have to buy any software. You load it up. No, all you need is a connection to the internet and you can get Google Gmail from anywhere. And you pay for what you want. You get tired of it, you shut it off. You're not obligated, you're not linked into them, you're not tied to them in any way. So that is software as a service. Now, platform as a service. This is a little sometimes it gets a little more difficult to explain. But a platform as a service is now, I don't want to own the operating system. I just want to be able to use an operating system to do something that I need to do, and then when I'm finished, give it back. And this is used really by developers, a lot for software developers. For instance, let's say if I'm not a gamer, okay? I am not a computer gamer. I know very little about gaming, but I try to use this as an example. If I want to write a new computer game, and I want that game to run on Xbox, I want it to run on my Windows machine, I want it to run on an Android platform and my iPhone. So to write that, I will need to have the software development kit for all of these different platforms for it to run on. Well, if I had to buy those so I could develop it on those, that would get pretty expensive. But instead, I do platform as a service. So where now Android will let me write my program on their platform and launch it myself. When I'm finished, I don't own that platform. All I want to do is write my code on it. So now that's platform as a service. I've got an operating system as a service. The third layer here is infrastructure as a service. Infrastructure says that I don't want to own hardware. Meaning, I don't want to own a server. I just want to buy server time. I just want to buy the ability to do processing. And you got many companies out here, AT&T, Amazon, AWS, they're probably the biggest in providing infrastructure as a service. So that, for instance, you can go out there and you can get your own instantiation, and of computing power. And you can set up your own databases and all that right there on the Amazon platform, and you don't have to own anything. As a matter of fact, Amazon will give you all 3 of these. So you don't have to own anything. The only thing you need to own is a device that can connect to the internet that you can get to the Amazon site, where they will provide you infrastructure as a service, they'll provide you the platform and the software all running together. And that's what we talk about. That's what we talk about a service delivery model. How can I get these services to the people that need them? That is really what the cloud is all about. Okay? And those, like I say, those are just the basic one. There is many. You can get storage as a service. As a matter of fact, if you've got Google, you may have Google Drive, right? Guess what that is? That is storage as a service, meaning that now you can store your files out there as a service as long as you want. If you need more storage, what do? You pay Google and they'll give you more storage space. If you need less storage, stop paying them. Guess what they do? They take the storage space back. So that is a service. You don't own any hard drives. You don't own any RAID machines and all this stuff in your house. Same with database, anything is a service, XaaS. So there's all these different things as a service. You're going to see that term quite a bit, but that's where it comes from when we talk about the delivery model. We also talk about the cloud. It has its own deployment models, different types of clouds. Now, we start with what? A private cloud. Private cloud is really used by a single organization. In my house, I have a private cloud, meaning my computers and everything is connected to a cloud. And why is it a cloud? Because I can get to it across the internet. I can be away from home and still log into my assets. So it's a private cloud owned by me. You can have a public cloud. For instance, Google. That's a public cloud. Everybody has a Google account. You can get access to their cloud. Then there's things like community clouds. Hospitals, regional hospitals. You may have 5 or 6 hospitals in a geographic area, then they all want to be able to share medical records. Or schools. You have universities or public school systems. And these public school systems, they all want to be able to share information together. And so they have a community cloud where they're able to share within the community. And then on top of that, you have what we call a hybrid cloud. A hybrid is a combination of any of those, private, public, community. Any 2 or 3 of those together gives you a hybrid. And honestly, that's how most of us operate. At home, I have a hybrid. Why? Because I have my private cloud at home, but I also have Google, which gives me public cloud access. Most businesses, they're the same way. They may have private clouds because there are certain things they want to keep inside, certain things that's valuable. They want to be sure that it stays inside. Whereas there's other things that they can put out onto a public-facing cloud. So now let's look at some of the components of a cloud. It starts with clients at the beginning of the process, and we have clients. Different types of clients: thick client, thin client, mobile client. Thick client. What a thick client is, that is a computer that has its own operating system, hardware, software, but it can still connect to the internet and get to the cloud. Like my Mac sitting here, the iMac. That is a thick client. I also have a thin client because I have an iPad. iPad doesn't have all the applications and everything that my iMac does, but I can still get to the internet with it, so that is a thin client. Now, and it also can be considered a mobile client as well because it's mobile. So when you think about thin clients, it just has very bare bones that you can just be able to do certain things to start it up, where you got a monitor, keyboard, some type of input-output devices. And mobile clients, like I said, we all have those, cell phones in our pockets. Well, now on the other end of the spectrum, over here, that's our data centers, and that's where our applications are being hosted. This over here, that is Amazon. That is where all their data is, all of our data that we want. And there may be many data centers. Just don't think of these as one single location. These data centers exist, all over the country / all over the world. The third part that makes these things work, though, is what we call distributed servers. Even though my data is back here, I now need a set of servers to be able to distribute it to the clients. And that distribution is done across the internet. So when we think about the 3 major components of cloud, it's client, data centers where we're applications, and the distribution server that actually distributes these application services to the client. Got it? All right, let's move on. So what are some of the characteristics of cloud? Well, one is really on-demand self-service, meaning that as a customer, I can provision it myself. I don't have to call anyone to come in and provision it. I can go out to Amazon, I can go out to Google, I can go out to Rackspace, I can go out to any of these places and provision my own service. Broad network access. I can get to it pretty much from anywhere as long as I have network access. Resource pooling. This is kind of more from the provider perspective. So now Amazon is able to resource pool, meaning they can use all of their servers together because when I get a Amazon site, they're not going to give me a whole server. No, all they're going to give me is processing time on a server, which is going to be shared with you and you and you and the person back there in the gray sweater. It's going to be shared with you too. So we're all going to share processing time. So now Amazon is much more able to better utilize their equipment, their servers. Rapid elasticity. Elasticity is a cloud word that we love because it means that we can expand quickly or we can contract back down. So when I need more capability, I can build up. When I'm finished, crank back down. For instance, if you look at Tax season. If you think about any of your tax companies, what's the one where you always see the people out on the side of the street with the Statue of Liberty suit on? Well, anyway, so coming around April, February, March time frame, guess what? These tax places get really busy. So they probably need more capability. So they're able to go to Amazon or Rackspace or any of these cloud providers and say, we need more processing power for the next 2 months. They write a check. Amazon provides them. Come June, tax season's over, they shut it off. Elasticity, able to grow, expand, and contract. And it's also measured service, meaning that as a cloud provider, they can measure your service. So for instance, with Google Drive, you start, they give you 15 gigabits free, measured service, metered service. If I want to get more, I can pay, I can get 100 gig of space. They can measure and meter your service. What about security? I know a lot of people are really fearful. Oh my God, I don't want to put my stuff in the cloud. It's going to get, somebody's going to see it. Well, two sides to that story. I always like to bring this up. So here's some of the advantages. The companies that do cloud, that's their business. That's what they do for a living. So guess what? They're going to be on top of their game. Probably much more so than I am doing my own security at home. So they're going to be sure that they keep all their software well patched, everything up to date, and they're going to hire the best. So if you talk to people who work at the Googles and Amazons, they're the better cybersecurity specialists. They're not just IT tech. So you just don't have Jim Bob from down the street working on your system. So there are advantages to using, because what happens, because if Amazon or Google or pick one of these gets a bad reputation, and get breached really badly, that's their business. They're losing big money. Now, what are some of the disadvantages for cloud provided security with your stuff in the cloud? One is jurisdiction, because you can't put a geographical boundary around this thing we call the cloud. Very diverse. And there could always be malicious insiders. And you're right, your data is there. Thing to always be concerned about from a business perspective, what we call vendor lock-in, meaning that you may be with one cloud provider and you want to switch to another, but you've been locked in contractually or from a technological perspective with this one vendor. So now you got to figure out, how do I get my data, all of it back, and know that the integrity hadn't changed on that, so I can now switch to another. So that gets a little bit tricky within itself. All right, we're going to switch gears one more time to technology. What are we talking about? One of the technologies that we use quite a bit from a cloud perspective and even at home is virtualization. Virtualization actually has been around for back in the days when we first started mainframes. Yeah, that's how long virtualization has been around. Now it's gotten a lot of traction in the last 8 to 10 years. With VMware and some of these many different companies, and even Microsoft, they build it into their operating system. So we're going to talk about virtualization. This is just kind of a pictorial comparing a traditional model of a computer with how we virtualize it. But we're going to break this down a little bit deeper. So when we think about traditional computing, in a traditional computing environment, we start out with hardware. We talked about this before. Your hardware consists of your CPU, memory, storage, network interface, your I/O ports. On top of that hardware, we said we install an operating system. That could be Windows 10, it could be a Mac OS, whatever. On top of that, we install application, our host, we call them host applications. Office, Visio, whatever your applications are. That's our traditional model. If you got a computer at home, I got one at home, that's how they traditionally work. Now and these are what we call the tightly coupled. They all fit together really tightly. Now, in a virtualized computer environment, we do something a little bit differently. We start out the same. We start out with hardware. You got to have hardware, okay? And then on top of that, we have an operating system and the operating system app. So up to this point, it looks about the same, right? Now, here's one of the things, though. Typically, most of this hardware isn't fully utilized, meaning that this CPU isn't running at 85, 90% of its utilization. Neither is the RAM or the hard drive. So we've got excess utilization here. So that's where the secret sauce come in. That's where we get a program that we call a hypervisor, or a virtual machine monitor, if you're working Windows. But VMware, which is a very popular company that does hypervisors. That's what they call theirs, is a hypervisor. Now, what this hypervisor does, it is a abstraction layer that we load on, and now what it does, it's kind of like a traffic cop. It says that, you know what, I've got about, look, it talks to the hardware and says, you got excess capability right here. So you're running this and you're doing great, but there's some excess capability. So I'm going to reutilize, or I'm going to reallocate that capability so that now I can install another operating system, or another, it just depends on how much capability I have, multiple operating systems, because the hypervisor is saying that, okay, we're going to use a portion of this CPU, a portion of this RAM, a portion of the disk space, the same network interface card, and we're going to make it look like it's virtual hardware. So this operating system, it don't know the difference. It's just, it's saying, okay, I see I got these components, I can install and I can operate. So that is what your virtual layer does. It doesn't affect the host applications, but now I've got a guest operating systems, and what I can do now is install guest applications on top of my guest operating system. So in effect, what I can have one computer, like my, let's say a Windows machine. It's running Windows, it's running Windows 10, and it's happy. At the same time, I can load Linux. I can load up Ubuntu. Or let's say if I have an older version of Windows running, I can load up Windows 7 or Windows 8 and run them all on the same platform. So that is virtualization. And really, like I say, the secret sauce is right here in that hypervisor software that's loaded. Like I say, if you get a Windows machine, especially Windows 10, it has the virtualization already built into it. Or, if you have a Mac, you can buy VMware Fusion, which is a virtualization software. And then there's some free ones, open source, like VirtualBox, that's built by Oracle, that will do the same thing with as far as virtualization. And that's just what we refer to as the abstracted layers. They're not tightly coupled. We kind of broke that coupling apart between here and inserted software. All right, so we've gone through a lot of things. Got a couple more. Mass storage. Well, because when we think about cloud and think about those environments, how we store our information has changed. When we first started out, we would call server-centric storage, meaning that every server, like in a data center, had its own storage assigned and attached to it. So let's say if I was, here's two storage devices in this server, two in this server, and two in this server. So I got a total of 6. But this right here is a print server. Now, print server isn't used that much, so it's really underutilized. This is my mail server. Man, everybody is using Outlook email, right? So this server right here is running at 85–90% utilization with storage. This one is running at 15% utilization. In this environment, I was not able to share those resources together. So I would have to end up probably buying more storage to make that work. Well, now we've gone into what we call an information-centric storage architecture. Okay, so what I've still got the same 3 servers, okay? 3 servers. Let's say this is my print server and this is my Exchange email server. Well, now I have moved the memory, the storage, the mass storage out of them, and I've built a storage network down here and it goes through a SAN, so you may have heard of that storage area network, or NAS. Some of you may have a NAS at home, a network area, a network attached storage. But this is a SAN, so now these servers, they don't know and don't care where their information is stored. And it could be on any of these 3. So now I can better utilize my storage because it's shared between all these. Unlike here, where the storage was very centric to each server. So now you see that we've changed up the model to an information-centric. So when you hear terms like SAN, storage area network, that's what we're talking about. Similar to NAS, network attached storage. That's where I attach. That's right, you probably do it at home. If you got a router that's got the USB port in the back, you can plug in a USB hard drive, and that is shared across your network. It's attached to your network attached storage. And there's advantages and disadvantages, meaning that it's scalable, a little more reliable, and things of that nature. Last piece we're going to talk about, and this is going to kind of blow through this pretty quickly, is networking. Because we're talking about hardware, software, but a big part of this is how do we connect up all these pieces. And this is how we do it in networking. Now, before we get into any components, we really want to talk about it from a modeling perspective. And if you think about a model, model is something that is an abstraction of something that's real. So the model that we use in networking is the OSI model, Open System Interconnection model. And really, it's a great way. It's a really powerful tool for diagnosing problems because it gives you a layered approach up and down the model to see where problems may exist. And it's a great language, a great way to explain or describe how your network pieces go together. Now, when we talk about the OSI model, and there's a couple different models, but we're just going to focus on the OSI model right now. There's the TCP/IP model, but for OSI, 7 layers. We can start at the top or bottom, either way. But yes, application layer, presentation, session, transport, network, data link, and physical layer. And the way that we always remember this in the networking world, all people seem to need data processing. All people seem to need data processing. But anyway, how do these fit together? Well, at each layer does something specifically. If we start at the bottom, layer 1, the physical layer, that's your cables. That's your Ethernet, that's your wireless. That is the physical infrastructure that makes your network hooks together. Layer 2 is, sorry about that. Layer 2 is kind of what we'll call a data link layer. It takes the ones and zeros, the bits here, and sends them to your NIC, your network interface card on your computer. We know where you got the little plug where you can plug in your RJ45 cable or your wireless card. This is layer 2. This is what we call layer 2. Layer 3 is a network layer. That's where we do routing, meaning that now I want to connect my computer to other people's computers, in other locations. And the routing layer is which figures out how to get it there. Layer 4 is transport. That is, I always like to equate it to a train. Okay, if you think about your data on the internet, it's a lot of segments of data. What the transport layer does is kind of like a boxcars. It puts them all together in boxcars, so now that it can be transported across the internet. And when it gets to the other end, it takes this boxcar and sends it that way. This one sends it the other way. So it's a way of packaging your data so that it can flow across the internet. The session layer, that's what makes connections. You have certain between applications, so that I can open up a session between 2 applications, and these applications can share information. Presentation layer is what gets your data coming from the application layer ready to be presented. For instance, if you think about things like JPEG and MIDI and PNG, those are some of the protocols there. And the application layer at the top of the stack, that is what interfaces with your user applications. So if, kind of working from the bottom down, top up rather, or top down, bottom up, either way we want to go. But those are the things that make up really how we communicate and how we talk about networking across the internet is really from a modeling perspective. And to work it down, I can give you an example like email. So if I want to send an email, well, no, let me back up. Let me use a different example. Internet. I want to get out to the internet. I got to open up Google Chrome and want to connect it to the internet. Google Chrome is a user app. Well, that user application talks to layer 7. And at layer 7, it uses what we call HTTP or HTTPS. You've probably seen that when you go to the internet, right? Well, that is an application layer protocol. Chrome, it can't really talk to the internet. All it can do is tell HTTP, hey, can you go to the internet for me? And then HTTP goes out, and it does, and it connects. And then you go to the internet, and you want to post a picture. Well, before we can send that picture out there are, within certain applications, say like Adobe, or say like Windows Media Player, or Windows Photos. It says, you know what? I'm going to put this in a format that the rest of the world can understand. I'm going to present it as a JPEG, or as a TIFF file, or as a PNG file. So that way, when that picture is uploaded, and I get it, and I want to download it, my presentation layer looks at the extension, says PNG. I recognize that. That's a picture. That's a portable graphics file. PNG, that's what it kind of stands for. Portable network graphics. So now it says I can read it. So it's been so I can present it. Session layer, here again, it connects up to two applications so that now they can talk to each other and can be transported across the internet. And this layer says, okay, I know where you want to go. It's kind of like the train analogy. Okay, you got your box cars hooked together, but now I got to get you on the tracks so I can get you where you need to go. And you're like the engineer, whatever, we got to switch tracks here and go this way. Got to switch tracks. That's what the network layer does as it routes things. And then the data link layer, it's like, okay, we got to be sure everything's prepared so we can go across the physical layer. So just like putting, your stuff on the box cars in the train. Well, it's got to be this size, got to be fitted this way so that the train can make it and fit on the track. So if we're going to put these layers to work in our house, like I said, those first, where they kind of fit. Those first top layers, those first four, really, they really are really part of your operating system for the most part. Now, when we look at layer 2 and 3, those exist in your router because most of us now in our homes, we have a combined device. It's really a switch and a router in that same box. So you look at this box right here. So that's really a switch and a router. It's a layer 2 and a layer 3 device together. But normally nobody knows that, really cares. And then as it goes out to the internet, we hit our layer 1, which is physical cable and a modem. As a matter of fact, if you got Verizon or some of these other internet service providers, all of this right here a lot of times is in one box, like BIOS. You got your modem, your switch, and your router all combined in one box. But anyway, and then that takes us out to the internet. So that's how those layers kind of fit together to get you to the internet. All right. Man, we covered a lot of information tonight, didn't we? Hope I didn't lose you anywhere along the way. But glad this is a video because you can rewind it, watch it again. Rewind it, watch it again. Rewind it. Yeah, you get it. All right, in summary, what did we talk about today? We covered components of a computer, the hardware, software. We talked about cloud computing, different technologies like virtualization, mass storage, and we touched on networking. Hope you kept up. Like I say, I always try to present something different than the PowerPoint that you already have because you already got those, and I'm sure you don't want to hear me stand here and pontificate on those again. So you can read those, but also watch these as well. Any questions, please feel free to contact me. You got my email, phone number, you give me a text. Really appreciate it. God bless you, and have a great week.